will be global? How do we do focal treatments, simulations? Alrighty, I gotta get rolling. I'm not kicking you out, but let me present, my friend. Okay, we could. Okay, guys, thank you for coming. I've finished my introduction. You guys all know me. I'm Dr. Silver. Nice to meet you. I wanted to talk about this. Okay, this was how life started on this planet. Long time ago, one cell. How that one cell got here, it's a great question. But the cell was living in a big pool, and that had to do two things to survive. Okay, from the beginning of time, every cell moves away from danger. It moves away from pain. We move away from toxins. We have receptors on the cells that pick up toxin, and then the cell would slither away from the toxin through receptors on the membrane. And then what did the cell also need to do to survive? Was it needed to move towards good. It needed to move towards food. It needed to move towards safety. It needed to move towards reproduction. So back a long time ago, that one cell had receptors that picked up where good was happening, had receptors that picked up where bad was happening, and it used that information to decide where to move, this way or that way. That was a long time ago. And over a long time, these cells started clumping together into multicellular beings, many cells living together. But then when it's 100 cells, how do they all move as one unit or not? They needed a thing that could be a receptor, a sensor of where the bad was, where the good was, and then tell all of them together to move. And that was when we got the first neuron on this planet. Just like the cell I showed you, the neuron is a type of cell that most living creatures have that has receptors on it. All of these little arms, and this is what our brain is made up of, is 100 trillion of these. 100 trillion of these are all working together all day perfectly to make you. And you have one consciousness between 100 trillion of them working together. It's so incredible. The neuron, these are called dendrites. And the dendrites receive information. They may receive information from other neurons, but they often are receiving information from the environment. Okay? These dendrites are sometimes turned on by chemicals. And the neuron can say, whoa, there's a chemical problem. And then it fires a signal down to tell something to move. Or to another neuron to say, this is what's happening over here, so you need to do this over here. And the whole brain is made up of these receptors. Receptors that listen what's going on, process what's happening, and then decide how we're going to move away from it. And so back when it was just when it was just cells, the receptors were on the surface. But as life went on and we got neurons working together, well, we needed to make receptors on the outside of the body. And so billions of years ago, when there was no humans, just fish, so fish developed a very interesting organ called the lateral line system. And that's what this is. This red bar right here is called the lateral line system. And what the lateral line system would do is that as the fish is swimming, the water would flow through that line. And if the water was flowing that way, then the neurons would bend. And the fish brain says, hey, I'm moving forward. But if there was no movement on that line, then the fish's brain says, I'm staying still. But if the water is flowing that way and it's pushing the neurons like that, then the fish's brain said, I'm moving backwards. Okay? It was a receptor. It's to tell the fish what's happening in the world outside of it. This is one of the very first receptors that ever developed on this planet, is a gravity receptor. Am I moving forward? Am I moving back? Am I moving up? Am I moving down? We need to know where we're moving in order to move. And so you look at the fish, it's a very simple creature. It doesn't have much to tell it about where the food is, where the safety is, where the danger is, but it has a receptor that tells it when forward and back are happening. And it uses the information from movement or gravity to say, this is how I need to move. And so the fish just has a straight line, just a spine, just muscles on it. And when the fish thinks it's moving backwards because of that system, it kicks its tail to move forward. It's a receptor input, the brain integrates it, and then it has an output in response to the environment. I think this is very, very, very important because the fish didn't have ears, and it didn't have taste buds, and it had very bad eyes. Before any other of our sensory systems developed, the very first one was the gravity system, our brain's sense of where am I in space. And that gravity system, being one of the first ones to developed with an output motor system to the muscles in the spine. It didn't have arms and legs and knees. It only had a spine. And so those two systems are connected. Fundamentally, where we are in space commands the entire spine and how the entire spine moves. Everything's based off of that. That's very important. But now the neuron needed more ways to tell what was happening in the world around it. Well, before we even say that, the neurons needed to be protected, okay? The neurons are the most important part of the nervous system, but they are like jello in your hand. They're very soft, very squishy, and they break very quickly. And so a long time before human beings and before arms and legs, and all we had was up, down, and kick, we got spines. Spines, I think, are the hardest thing the body can make, and it makes that around the most important thing that it needs to protect, which is always the spinal cord, the nervous system, the brain. Look at where the bones are long time ago, just on the spine, and then the skull. And none of our other organs have as much protection as the nervous system does, right? It takes a lot to get through the skull, but it's very easy to get to the gut. The body puts, I call, biological investment where it's needed the most, the nervous system. And so the fish needed more to know what was happening around the world. But I said the only type of cell that gives us information is the neuron. So the neuron, it pouched all the way out through the front of the skull into the eyeball. And if you look at the eyeball, all of this is nervous tissue. And the nervous tissue comes out and it goes along the back of the eyeball. And the rest of this eyeball is just a focus light on the neurons, on the cells. And the neurons, they take the light, and they turn it into electricity, an electrical signal. Every neuron in our body works this way. I feel smooth. Smooth is converted into an electrical signal that goes up to my brain, and my brain interprets that electrical signal as smooth or rough. But it's always electricity in between here and here. And so the fish made an eyeball, another type of receptor, but this time an organ, a more complex receptor, to see visually what's happening in the world around it. But now that the fish had an organ to see, it needed a part of the brain to interpret what it was seeing. And that is the entire brain's job, is what is going on in the world around me? How do I integrate that into what I think the world is? And how am I going to move in response to the world? That's the job of the brain. That is the job of the unconscious brain and the conscious brain. So the unconscious brain moves towards good and bad, whether you're thinking about it or not. The conscious brain says, that looks good, and it moves the body. But before we even start to move, I start to move my hand to grab that. A long time before I move my hand to grab that, my leg fires to stabilize me so I don't fall over. If my leg didn't activate, I would fall over. So it's unconscious activity of the nervous system, and we need a good balance of that, always. And so we develop many more organs that are really just receptors of the environment. We got ears, so we could hear the environment. We got taste buds much later on, so we could taste the environment. Because before we had receptors to sense the environment, the brain is just trapped in black. It's trapped in the skull in darkness. And it is our brain's interpretation of these receptors and this electricity that forms what we think of as reality. And for me, I see the table over there with my receptors. I feel the tables over there with my receptors. So when my brain says walk to the table, I walk, no problem, straight to the table. But if somebody's eyes are shifted this way, they see the table as over there. And the receptors are broken. To them, the table is over there. To the rest of us, the table is right there. It's the same reality, but it is how our brain constructs the sensory input that we make the reality. So the person with the eye shifted left, they see the table there, they want to walk to the table, they walk like this. They make wrong movements. And what happens when we make wrong movements? I want to reach for this, but I make a wrong movement, I reach here instead. It hurts. I use my body incorrectly, and I have to make compensations to do what I'm trying to do. And it's not because of voluntary issue. It's because the involuntary system, the leg stabilizing, isn't working sometimes. Sometimes we can train it, sometimes we can't, sometimes that's my job. But this is how the nervous system was slowly adding pieces onto it, one little bit at a time, starting from trapped in darkness, I can only move forward, back, to I can see the world, I can hear the world, I can taste the world. But we were still very midline. We were straight. Fish were straight. And so later on, as we start to grow limbs, we start to grow this way with our bodies. Well, where were we going to process the information for controlling our shoulders and our hips? We never had shoulders and hips before. The brain grew out this way. So the things that are in the middle of the brain are very old. Like the middle of the brain right here in the cerebellum, this middle part is called the vermis. That was very early on that part of the cerebellum existed, and it controlled the spine and it controlled the eyes. But a couple million years later, we got shoulders and elbows. The cerebellum grew this way. And this part of the cerebellum over here in the hemisphere controls coordination of our shoulders and our elbows and our hips and our knees. And a very, very long time, much later, human beings come and we get hands. And we needed a new part of the brain to control our hands. But there was no way forward or back or up or down to grow, no room, so the brain grows sideways. And this very, very outside part of the brain, the cerebellum right here, controls coordination of our hands. And you don't see that part of the brain in fish. They don't need that part of their brain. It's as the brain developed, it added parts, added parts, added parts. And so here we are today as human beings. This is what we look like on the inside if you remove all of the bones, everything except for this nervous system. The nerves go everywhere in the body. And this picture doesn't show the receptors on the skin. All of my skin is loaded with receptors. Light touch, deep touch, smooth, pain, hot, cold, pressure. If we could see the receptors on this body, it would look like a human being. They're everywhere. And this is the one system that talks to every part of our body all day, every day, is the nervous system. Everything that we move, everything that we feel, all happens right here. And when I stub my toe, there's a second before it hurts, right? It takes a second for the signal to get to my brain. And pain is processed in the brain, not in the toe. Toes don't think. Toes don't think. So I love this line. I've said it a million times. Our perception of our universe is not a true representation of our physical universe, but a mental construct composed by our mind's interpretation of all the integrated nervous input available to it at any given moment. And what that means is that reality is individual to each one of us. This room is a different room to each one of us. I've been in this room a million times. I have an emotional connection to this room. He doesn't. It's the same room, but a different reality based off of what we can see. And then you take a blind person and put them in this room, and it's a totally different room to them, but it's the same room. Reality is what our mind makes of the input available to it. And sometimes the brain has good input. Sometimes the brain doesn't have good input. And if the brain doesn't have good input, the brain doesn't have good output. I say garbage in, garbage out. If you get bad input in, then you don't know how you're supposed to function on the other end of it. And so I break the brain into two halves, the top half and the bottom half. The top half is above that yellow line. The top half of the brain is what I call the house. The house is where you live. It's where you hang out. It's where you eat your dinner. It's where you watch television. It's where you enjoy your life, is in your house. And so we'll explain all the parts of the brain and what they do in a moment. But below the yellow line is the brainstem and the cerebellum. And I call those parts of the brain the basement. The basement is everything you need to run the house, but you don't want to see, like the water heater and the electrical board and all the stuff that keeps the house going. So our brainstem really controls all of our non-volitional activities, things that we aren't voluntarily working on. So breathing, right? Breathing is both. You can control your breathing, but normally you don't have to think about it. It's involuntary. It's mediated in that brainstem. Heart rate in the brainstem, posture, balance, eye movements, and all of the nerves to your face and head come out of your brainstem. So think about it, voluntary, non-voluntary. I tend to work on the non-voluntary part because when people have concussions, they have head injuries, the majority of the damage happens in the brainstem. However, everything we feel, you touch this, there's a moment where that signal from my hand goes up my spinal cord, and anything from my body that I feel or touch goes up the spinal cord through this pathway up here, and it goes to this area called the thalamus. And the thalamus is a little egg deep in the middle of the brain that we call the gatekeeper. Everything has to go through the thalamus before it gets to the brain. So anything I touch or feel or pain in my body comes up, synapses in the thalamus, and then goes up to this part of the brain up here called the parietal lobes. And the parietal lobes are where we feel things. So when somebody touches your hand, there is electrical activity in your brain right here. And if I take an electrical probe and I put it in your brain right there, you feel like somebody's rubbing your hands. That's the delay. And sometimes people will have problems in sensation. They feel like somebody's touching them, or they don't feel like their body's part of themselves. Not because there's anything wrong with the body, but because of a parietal lobe problem. Because their sense of their body, where they process their sensation, is broken. I fixed 2 of them this week, actually. It's a new thing that we're working on, is how do we rehab these lobes of the brain? When we have vision, when something hits my eyes, there are receptors in my eyeballs that turn light into electricity. It sends that signal back to the thalamus. Everything synapses in the thalamus, has a little pit stop there, because the thalamus is trying to get rid of extra information we don't need. That's what its job is doing. It's filtering too much information. So when it goes through the thalamus, there's less for the occipital lobes to process. And that's where vision really occurs. The back of the brain right here processes vision. And when I say processes vision, it says, what is the color of this? What is the size of this? How far away is it from me? What do I remember about that? Is it a rock? No, that's a mouse. I remember that. All of that happens in my occipital lobes. And so sometimes you will have a patient with vision issues because there's a problem with their eyes. But sometimes a patient's been to the eye doctor and they can't find anything wrong with their eyes, and it's because where they process vision is damaged from head injury, from many things. I have a girl right now we're treating who I believe has an injury here. She has double vision. She sees 2 of everything. Even when she has one eye open, she sees 2 of everything. Doesn't matter which eye. It's impossible for an eye problem to cause that. It has to be visually processed in her brain. So we're coming up with strategies to stimulate that part of her brain to make it healthy again. Because the brain is like a muscle. The nervous system's like a muscle. It's use it or lose it is the whole principle of the brain, right? The body, it's very conservative with nutrients. It doesn't have extra nutrients to spare. So the body's only going to put nutrients in growth into whatever you're using. So if you do bicep curls on the right side every day, the body says, hey, that bicep needs to be stronger. And it sends nutrients in there to strengthen up and make a bigger, stronger muscle. And the same is true with the brain. If I was to get massage on the left side of my body every day, but never the right side of my body, my parietal lobe would go bigger, like a big muscle. It would get more efficient because I was using it more. Use it or lose it is the principle of the brain. So anything that we fire over and over and over, we get better at. It's just how we learn any skill, right? First time you played soccer, probably not very good. Second time, a little bit better. Third time, a little bit better. Millionth time, professional. Because we fire those circuits, and every time we fire those circuits, the brain makes them a little bit more powerful. And so all vision is done in the occipital lobes. Sound and taste and balance go up. They fire in the thalamus, and then they go to the temporal lobes, these parts of the brain on the sides. Okay, when I hear a pitch, that sound goes to my eardrum turns it into electricity, sends that over to this part of the brain. What does it mean? Is it close? Is it far? Is it Is it Is it bad? Is it a bear? Or is it, my baby calling for me, right? All of that happens in the temporal lobes. The meaning of the sounds, the meanings of the smells. These smells, they remind me of grandma, these cookies. You remember, you've heard that? Why? Because smells happen in temporal lobe and memories happen in temporal lobes, right next to each other. That's why smells and memory are so close, as they happen in the same part of the brain. And smells are very, very powerful because I said everything goes through the thalamus except for smell. Smell goes straight back to the brain. No gating on smell, making it one of the most powerful senses. I have a patient right now, he lost his sense of smell during COVID. He's never gotten it back. I think it's a temporal lobe issue because when we have him smell things, if we stimulate this part of his brain, it comes on a little bit better. He's tried a million things to treat his nose, but it's brain-based. And it's a different model of thinking about the body. Because everybody's looking at the knee. What's wrong with the knee? I can't see anything on the MRI. It's nothing is structural. It's electrical. We have electricity up and down all day, millions and millions of signals, and you can't see that on an X-ray. But you can see it through movement, which is what I do. And so you have all this information now. What am I seeing? What am I hearing? What am I smelling? But it's all in different parts. It all comes together right here at what's called the PTO, the parietal temporal occipital region. It takes all of that and puts it into one place. This is what I'm seeing, smelling, hearing, feeling, and gravity, all in one place to combine it. And then it takes that information and it sends it back to memories. Okay, do I remember this? Have I been here before? Because what this is just a piece of paper. But because of my experiences growing up, I know this is a magazine. So we apply our reality to our memories, always, to create reality. What we're seeing, what we're feeling, what we're smelling, we create to our memories. I have, an example of a gun. To some people, it is a good thing, and some people it's a very scary thing, but it's the exact same thing, right? It's because we're taking what we feel the gun, we see the gun, and we're comparing it to memories we have to form reality. We take this concept of where we are, this reality we've done, and we send it to the very front of the brain called the prefrontal cortex. And the prefrontal cortex is the beginnings of movement, right? I see Maria there. I know Maria. I have memories of Maria. What am I going to do? Okay, goes up to the front of the lobe. And it thinks before I move to Maria, it plans the movement ahead of time. What if I give Maria a hug? That would make her happy, right? But it also does social acceptability, social awareness. What if I stood up and gave Maria a kiss? No, that'd be weird. Don't do that. The prefrontal lobe processes, is it appropriate socially? Should I do this? But also, what will happen later if I do this, right? Because the animal brain is very aggressive, right? Animal brain says, I see Al, he's another male, punch him, right? But the human brain, the frontal lobe, we're the only creatures that have the frontal lobe. Human beings, it's just for humans. The frontal lobe predicts the future. It says, Josh, if you punch Al, he's probably going to punch you back much harder. Don't do that. It predicts the future. It predicts social acceptability. It predicts your movements before you even do them. And then it's time to move. Only then is it time to move. So it takes this, yes, okay, let's walk over to Marie and give her a hug. Sends that signal up to the motor cortex. Motor cortex is right here. And the motor cortex says, okay, Joshua, if you're going to go give Maria a hug, you're first going to need to move this leg. And you're going to need to move this leg. The motor cortex just does the movements. It just says, move this part of your body, move this part of your body. But the movements are very sloppy to get to Maria, okay? And when do I start the movement? Go, right? When do we start? So it takes this information for movement. And movement, there's only 3 types of movement because that's the whole human experience. What do I see? What am I going to do about it? 3 types of movement. I'm going to move my body, or right here in Broca's area, I'm going to move my mouth to say Maria. That's where movement of your mouth comes from, is the frontal lobes. Or right above it, there's the frontal eye fields. I'm going to move my eyes to look at Maria. It's always about movement. That's the only voluntary interaction us human beings have with our environment. Always skeletal muscle movement. Takes that signal, sends it to the basal ganglia, and the basal ganglia is a part of the brain that's the red light, green light of the brain. So it said, okay, you want to move to Maria? When can you move that leg? Now. And it gives the green lights for movement. When I get to Maria, I have to stop moving my body. Red light, that happens in that part of the brain, the basal ganglia. It stops movement. When patients have a problem with their basal ganglia, they tend to get seizures or tics or movement or Parkinson's because they can't stop movement, they can't start it. There's another form called chorea. Chorea, these patients, they'll do this. They just can't control it. It's because the basal ganglia isn't working. It can't put the red lights on movement. And so now we can start the movement, but the movement's very drunk, very sloppy. And so that information goes down to the cerebellum, and the cerebellum is the computer processor of the brain. It takes all the signals and cleans them up into one coordinated signal. If I'm going to walk to Maria, I don't need to move my leg here, here, and here to step. I can coordinate those muscles into one nice movement. Coordination. When people have problems with their cerebellum, they become uncoordinated. And so they may miss their nose, they may miss objects, they may drop things, they may be clumsy type people, but cerebellum coordinates balance. So they tend to have more balance problems when they can't coordinate the muscles involved in balance. But also, like I said, the cerebellum, the outside, is controlled to the hands in human beings. Well, the hands and the frontal lobes are connected in the cerebellum. Because this is new. And so the cerebellum on the very outsides, one of its jobs is coordinating hand movement, but coordinating thought. And when people have cerebellum damage, sometimes they can't think straight. They can't think clearly. Their thoughts are discoordinated because a part of their brain is not firing correctly. It's under functioning. It's not dead. It's not damaged. It's just depressed. And it's okay if a neuron is depressed. We can rev it back up again. If a neuron's dead, we can't revive the dead. But the thing is that we all possess an incredible ability for our nervous system to grow. And it's called neuroplasticity. And we'll talk about neuroplasticity. But before we do that, it goes down to the cerebellum. Cerebellum shoots it back up to the frontal lobes. It goes down to the body. And finally, the body moves. That whole circuit, I see the table, I want to move to the table, that whole circuit does that much. That's it. For me to get this whole thing, that whole circuit happens 1,000 times instantly. How incredible is our brain? Because the second I take my first step, my eyes see something, the whole world's different. My body feels different. I need to create a new motor program based off of my new reality of being here instead of being here. And the whole thing repeats thousands of times per second. It's unbelievable how cool our brains are. If I want to reach up and grab something, before it even gets to my conscious mind, the motor loop has happened 13 times before I even think I want to do that. And so the right brain controls the left side of the body, the left brain controls the right side of the body. The brain is crossed. I was actually this last week curious, why? Why? So I did a lot of research on this. I saw two interesting theories. One theory, it said there was an early vertebrate, and it's got its head twisted around, and somehow it survived, and it was advantageous, and all of life came from that one early vertebrate who got its head somehow twisted around. That's a theory. I don't think that's possible. What I thought was a much better theory was shared information versus separate information. My brain wanting to voluntarily move the right side of my body, that's a separate information. But when my brain wants to move the right side of my body, it still needs to stabilize the left side of my body. That's shared information. And so the brain has cross tracks for information that needs to be kept separate, like move the right hand. But information that needs to be shared, like how to maintain balance when we do that, it has ipsilateral pathways that go down the same side. I thought that was very fascinating. And so either way, this is how it's supposed to work. Right body to left brain to right body. And so every neuron in this whole nervous system contains an amazing ability called neuroplasticity. And I like to just read this. Neuroplasticity is the process by which the brain changes in response to experience. It is the brain's inherent ability to rewire and modify its neural structures to accommodate new information or conditions. This means that learning skills, recovering from an injury, and adjusting to physical or mental challenges all rely on neuroplasticity. I talked about use it or lose it earlier, right? The muscle gets thicker. When we use any neuron over and over and over again, eventually that neuron becomes so stimulated that it starts to grow bigger. It gets bigger, it grows more connections to other neurons. One arm, it can only push with one arm, it's half as powerful if it can push with two signals at the same time. Eventually, that neuron is pushing 10,000 signals at the same time as it keeps getting used over and over and over because it's got a high demand on it. And so every neuron in the whole brain is capable of this process. And this is how we learn things. Okay, did you guys learn anything today? Neuroplasticity happened in your brain. When you learned, you made a new connection. Oh, fish have lateral line system. There was a new connection made in your brain for you to even remember that. For you to remember my name, neuroplasticity happened. But it's how you learned your trade. It's through growth of neurons. Every neuron is capable of this, and it's how the brain heals from injury, but it's also how the body heals from injury. We have a spinal cord stroke and the person is paralyzed. 6 months later, they have more movement. How? The spinal cord was cut. It's because the neurons grew new connections around the injury. And so we possess this inherent ability, and it's all based off of a hormone called BDNF. BDNF means brain-derived neurotrophic factor. So whenever I'm going to be learning tennis and I keep practicing tennis over and over and over, at one point it's so intense that it's time for the neurons to grow. My brain releases BDNF. It's a hormone of neuroplasticity. And so I read this really cool book called The Neuroscience of Enlightenment about 15 years ago. And it was written by a shaman and a neuroscientist on how do you release BDNF in your brain, brain-derived neurotrophic factor. The neuroscientist says, well, we can create neuroplasticity by doing things that do that. But the shaman says, well, that's what we're trying to do with shamanism, is create enlightenment. Maybe enlightenment is neuroplasticity. You look at the two. Shamanism, What do they do in shamanism? They do Om, right? You look at medical neurology, they study Om. When people do that, their vagus nerve increases activity. Yes, it's the same. It overlaps. So they made this entire book and this entire cleanse on how you can increase neuroplasticity in your brain, and it's based off of 4 rules: repetition, intensity, salience, and caffeine. That's what I learned from them. That's what I learned from my neurology mentors. It's how do I learn any skill? How do I learn tennis? Well, the more you get out there, the more you repeat it, the more you repeat it, the more you practice, you're going to get better at anything you do with practice. Number 2, intensity, okay? If you go out there, but if you go out there with good intensity and you're really trying to get that ball and you're giving it your hardest, your brain will grow faster because you tried harder. Intensity helps the brain grow faster. Repetition helps the brain go faster. Salience. Salience is how much I care about this. Tennis, could care less. I love tennis. If you love tennis, you're going to have better neuroplasticity. Your brain's going to grow faster about it. And so there's so many ways to do all of this. But no matter what you're trying to help your brain grow in, you have to make sure that it's enjoyable. It's kind of why I say exercise, the only rule is that you enjoy the exercise you're doing. I don't recommend yoga because it's best for plasticity. I recommend soccer because you love soccer. I recommend kayaking because I love kayaking, because I have salience for it. It's how we build anything. And then caffeine. There's just so many studies now that say caffeine's good. It's good for your brain. Too much is bad. Too much water, you drown. Too much oxygen, you light on fire. Too much caffeine, bad for you, but a little bit is very, very good for the brain. It's a great reinforcer of the brain. It makes anything you do have more salience if you're caffeinated. You go to the gym, I hate going to the gym, but if you are on caffeine and you feel good when you go to the gym because of the caffeine, your brain thinks, I think I like the gym. And it builds salience towards any activity you do, which pushes plasticity and makes you more efficient in learning whatever it is that you're studying. So these are the rules for everybody. However, it's very interesting that when you look at basic human activity, things we should be doing, okay, fasting. Fasting is something I'm very passionate about, and it's something shamans did for neuroplasticity and enlightenment, right? It's something the Jews did. We do Yom Kippur. We have Lent. Every religion fasts when it comes time to become closer to God, right? The studies show that intermittent fasting, we do these fasts, it improves brain-derived neurotropic factor. Your brain releases more plasticity hormones when we fast. It exists science that explains the shaman practices we've done for so long. And so for me, this is my number one personal health maintenance thing, is intermittent fasting. Every day, I try to go 16 hours without eating, and I try to eat for 8 hours a day. And I have patients that they'll do 2 days on, 1 day off. There's a lot of different ways to fast, and there's no one right way to fast. But I recommend that you at least try it, because it's so good for your brain. Because, right, you eat lunch and you come back after lunch sleepy, but those days you don't eat lunch, maybe you're a little hungry, but you're focused. Big fan of that. Number 2, exercise promotes the expression of BDNF. Exercise is good for everything, but if it can help your brain release more plasticity hormones, exercise is good for learning, exercise is good for memory, exercise is free, and it's good for the brain. Serum BDNF concentrations show strong seasonal variation and correlations with the amount of ambient sunlight. Vitamin D, sunlight. How much sunlight did our ancestors get? They were outside naked all day, okay? Today, these days, I may be outside wearing this for 10 minutes if I'm lucky, walking to and from my car. We do not get the amount of sunlight we were designed to be getting, and because of it, our vitamin D is dropping, and because of it, our BDNF is dropping, and because of it, our brains aren't as efficient. And so that's okay. Sunbathe, but take vitamin D. I think every human being needs vitamin D because it will help their brains, it will help their immune system, it helps everything. And the very last one is curcumin. Curcumin comes from turmeric. Turmeric is my favorite medicine in the whole world because it has so many research papers now for inflammation. Usually I just give it to people for pain. But the research keeps saying that curcumin helps neurodegeneration, Alzheimer's, Parkinson's, MS. They all do better with curcumin. Why? It's because curcumin stimulates BDNF. BDNF makes your brain grow. It's one of what I call the core four. Every American should be taking curcumin every day for their brains, for their joints, for their blood, for the anti-cancer benefits of it. I could go on and on and on. And so I said, I'll give you something you can do, and then I'll tell you a little bit about what I do. I do functional neurology. You guys have all seen functional neurology. You guys haven't. But functional neurology it's the healthcare specialty we do here. And we're looking at the nervous system with it, and we're looking at the receptors with it. And we're trying to say, is it a healthy neuron or is it a sick neuron? Is it giving your brain good information about the knee? Or is it telling your brain there's too much pain happening in the knee or too much pressure? And you feel whatever your brain is telling you. And so you try and get the knee better, but there's nothing on the MRI because it's a neurological injury. And so that's how we work with our patients here. We're a healthcare specialty focused on the assessment of the nervous system, but we're looking at functional lesions. And a functional lesion in the nervous system is different than an ablative lesion. An ablative lesion means the nerve is dead. It's dead. There's no pulse. But a functional lesion means the neuron is just quieted down. It's gotten damaged. It had a trauma. It went into a state of depression, but it's still alive. It's just downregulated. And we call that a functional lesion. That's what I look for. That's what we fix with this specialty. We utilize the flexor withdrawal reflex for assessment and diagnosis of receptors in the nervous system that have become downregulated. The flexor withdrawal reflex, what is that? That is the flexor withdrawal reflex. We talk about this in neurology. When you touch a hot stove, you pull away from it automatically. Why? It's because the pain signal goes to your spinal cord and then it fires down to pull your muscles away from bad. Just like I said, life moves away from bad. We all have this reflex. And so what happens is when we stimulate the brain, if they pull away like this, we know there's a problem. And if we stimulate the brain and they're totally fine, we know it's an okay part of the brain. And we can utilize this. It's called muscle testing. I do muscle testing here, but I'm really just using the flexor withdrawal reflex to test this black box hypothesis of the brain that I told you guys about today. Sensory in, motor out. That's all it is. And we can use neurology, the motor, the withdrawal reflex, to tell how the brain's integrating that sensory input. Does that make sense? It's a lot. We use stimulations, deep tendon reflexes, and laser to reset neurons. And so it depends what the neuron is. If it's a sick neuron here and it's a stretch type neuron, then we stretch it to stimulate it. But if it's a contraction type neuron, we tap it because that stimulates contraction in the brain. But if it's a pain-based neuron, we slap it. That's how you stimulate a pain-based neuron. And if it's a hot neuron that's become diseased, I put a heat pack on there. And the whole body gets weak when the heat's on there. And I take it off and they get strong again. And we know that's a sick heat neuron. And we're able to diagnose where it is, what it is. But then how do you treat a sick heat neuron? With stimulation, you put the heat on it. You put the heat on it. That's the only way to wake that neuron up, is to use it or lose it, to put the stimulation on it. But we find a way to make it okay. Can't handle the heat, but the body can handle the heat there if we have pain here or cold here. There's always a compensation the body makes. And the treatment is always, you find the problem, you find the compensation, and you combine them. Because there's a theory, there's a principle called things that fire together, wire together. It's a very famous law in neurology. If you do any two things at the same time, they become connected. You listen to music while you practice juggling. When you hear that music next time, you'll think about juggling. You wired them together. It's the principle of brain. It's how we treat the body here. And so And that is specialty number 1. Specialty number 2 is we do upper cervical care here, where we're looking at the top 2 bones in the neck, and we put the head on straight, perfectly straight. Because if there's a problem here, it's going to choke the nervous system. Right here where the spinal cord is, right there. Right there, if there's a misalignment here, it can start to pinch on the nervous system. And forget what we feel and what we integrate. The whole pathway that it goes through becomes compromised. And this can affect the whole body. So when we do the adjustment to the upper neck, we take pressure off the core right there, the whole nervous system works better. It's how we treat the nervous system structurally, but then we treat it functionally by fixing the neurons in it. So this is kind of how we do it. Maria, we did this whole process on you. We have a CT scanner here called a cone beam, and I can take pictures like this here at the clinic. And off of this image, we're able to measure how misaligned the bones are. We're able to measure the best angle to do the alignment at. And it's different for everybody. You know, when I was in chiropractic school and they said, yeah, this is how you fix this bone, you just... I said, that doesn't look safe to me. But I found this method. This method allowed me to not just feel what was going on in there, but see what was going on in there, measure what was going on in there, and figure out how to fix it. So when we come to fixing these in our clinic, we have a machine, and we take the machine and we aim it at a very, very specific angle at that bone. It's different for every patient. We set it just to the perfect angle, and the machine does a little tiny tap, and that bone slides right back into place. And this slide I used to love. I would just play it over and over and over again, because that's what happens. You don't feel anything during the adjustment because it's barely a tap, but as that bone shifts back in, it opens up the neural canal and the body's able to heal more effectively because the nervous system can work more effectively. And the nervous system is what coordinates healing in our bodies, right? Long time ago, when it was just whales, how did the whales heal? No doctors. Healing, right? All animals have always relied on healing, and we somehow now live in a time where we think the only way to get better is with doctors. Okay, we can heal ourselves if we get our brain to work more effectively through some of the things I taught you here. And if you can't find how to do it on your own, then that's what I do. I can get straight to the end of it. So that's us. We're neuroplasticity. We specialize in human beings with nervous systems and spines. I thought that would be fairly general, but really we do migraine, concussion, dizziness, and pain are my specialties, but patients come in with everything: knee pain, back pain. I can apply the rules of the nervous system to the whole body, and this is how I like to treat a lot of pain. We do neurology, and the neurology is really an amalgam of about 6 different techniques I've learned over the years: quantum neurology, PDTR, functional neurology. I mix all of them together when I'm treating the nervous system to rewire it. We do upper cervical, like I showed you, but we have the CT scanner, and that CT scanner is the first one in North America. We're pioneers in the world of upper cervical here, kind of teaching the whole industry how we'll be using this imaging. So that's really cool stuff. We do chiropractic most visits. We do spinal decompression. We have that now. Spinal decompression is a machine that kind of straps you in like this and pulls you apart. So it's really good for disc herniations. So my friend Dr. Michael Fahim works here with us, and that's all he does. Me and the rest of us, we do neurology, we do chiropractic. He does that. And then I also have a really cool program here called the NeuroBoost program. And the NeuroBoost program, it's like an hour-long, I call it an IV drip for your brain. So you come in, we give you the brain tea, we give you a brain supplement, and then I have 3 different helmets you wear, and all of them stimulate the brain. And so it's about an hour long. I think it's a good thing for memory, focus, sleep, depression. I think there's a lot of applications we can get out of this NeuroBoost. And then this area is called the pharmacy, just because they left us a sign because of our mentors and people that came before us. I call this room the pharmacy. I like to do these classes, and so I want to do classes like this kind of regularly. If you would like to teach a class, I would love to have you teach a class. And I want to really kind of make a healthier St. Pete is my intention with this clinic, not just a chiropractic clinic, but somewhere where we work on the nervous system, but then we support sleep, nutrition, exercise, everything the body needs to heal from within, to be truly holistic. So as a thank you for coming, I just printed these little cards. They're not here yet, but I'll honor them. I was going to give you guys all $25 off a new patient exam if that was something you wanted to get started. It's just a little coupon for 25 bucks off. I'll just tell Jenny, or else I can set it up and she can take that off, but none of you guys need it. So if you guys want, I'll give you 25 bucks off on a sticky note, okay? Okay. I'll have my little cards next week. It just Canva's too slow. Otherwise, thank you guys for coming. That was the class. Very good. Thank you. So, how do we do on time? Pretty good.